So, what would people like to talk about? Oops.
Can we quickly review hysteresis? Because I only understand
Hysteresis,
it.
yes.
Yes.
Okay,
Hysteresis.
yeah, so hysteresis, so bifurcation diagrams in general, right? So, let's draw the standard hysteresis one. So this is some parameter, and this is some steady state value. So this is showing the steady states. And so the idea of hysteresis is that this is changing, whatever parameter is changing in time or being selected for. And so, as we said, if you start at any value of x in this region, and the parameter is fixed, all you can do is collapse onto the steady state. So if you were over here, you'd come down to there. So if your initial conditions were out here and your initial parameter setting was out there, you'd end up here after a little while. But now once you're on there, if this starts changing, what happens? So if we reduce it, we just keep marching along the steady states, until it gets to this point. When this solution branch disappears, then what happens? Then we would go quickly up to this branch, and then if we start, and then we decide we're going to change R the other direction, then we march back on this branch until we got there, and then we drop off. So the point is there's, what hysteresis is that even though you're always riding on a steady state solution, you don't have the same steady state for the same parameter setting. So it's closely related to the concept of multiple equilibria for a given parameter set, because here we've got 1, 2, 3 steady states. Okay. And so among those 3 steady states, the outer 2 are the stable ones. We've done that a bunch of times. But the point is as R is decreasing and R is increasing, we're riding on different solutions. So the concept of hysteresis, the simple statement of what hysteresis is it is when the steady state is not like path independent. It depends on the past values of the parameter as the parameters are changing. Does that make sense to everybody a little?
Is there like any other shape of the background?
Yeah, so we could have also done, you could also do one like this, with this one being unstable, and then you might come this way and then drop down and go back this way. There are lots of other shapes. So if you have 2 steady states, at least 2, that are simultaneously coexisting, and you're going back and forth when they're popping in and out of existence, that's when you are likely to get it, or that's when you will get it.
Can I? Because my main confusion is that I feel like I understood that, but then when it came to the homework, the multiple diagrams, I didn't.
Yeah.
Can I just go and show the one that I'm really confused about?
Yeah, please. That's great.
Very similar to one you just did. This one?
Oh yeah, this branch, yeah.
It doesn't?
So let's think about it. So this is the one that's the pitchfork. So here's R, here's X. So what do you think? If I'm over here and I go this way, I'm gonna go one of these directions, right? That's something that's not quite hysteresis. But suppose I go in the upper branch and then I go to here and then I come back, what's gonna happen? I'm just gonna stay on here and go back. So did that exhibit hysteresis? It's the same in both directions. So that's not hysterical. Not to be confused with hysterical. Hysterical, right? I also could have ended up going this way, and in practice with this kind of a system, there's something that would happen at that joint called spontaneous symmetry breaking, which is like, it could be an even chance that you go either direction, Or it could have something to do with the fact that you're not exactly at the steady state. So you still, if you suppose you started above, then you were just a little bit above when you got there. You wouldn't quite be all the way there, then that residual might be enough to kick you one way or the other. But that's not the same as hysteresis. Does that make sense? I can make the system hysterical by pushing that branch up like this. And that would have been totally allowed, except it would have changed this one to stable and this one to unstable. And then we would have had hysteresis, because if we somehow got up onto this branch, we came back. Does that make sense to everybody? So it's just the idea that you go up and you go down following the solution state, and is there a way that you can jump from one branch to the other so that at the same value of R in one direction, you're at a different value than in the other? Hysteresis is definitely not a general characteristic of nonlinear dynamical systems, but when you find it, you do know that it's a nonlinear dynamical system. So people look for hysteresis, and then when they find it, they say, we have a proof of nonlinearity. So there's that. So how do we know that hysteresis is not a characteristic of linear systems? Why does that system not have any hysteresis?
Like a linear system couldn't just randomly change like that, right?
Linear systems can't gain or lose solutions, and they only have the possibility of one solution, zero solutions, or all spaces or solutions. So in none of those cases can you get hysteresis. You have to have kind of a finite number of coexisting solutions for the same parameter settings to have hysteresis. And so that's a characteristic that shows that the underlying solution space has to be nonlinear. So we could do a Taylor series near here, and then we would find just one tangent. We could do a Taylor series near here, and we find just one tangent. We do a Taylor series near here, we find just one tangent. But we wouldn't find any Taylor series that had both of those two solutions on at the same time, right? That's the key. That's a key distinction between the linear systems and the nonlinear systems. So multiple equilibria for the same parameter setting, hysteresis, are two of the characteristic features of nonlinear systems. People always think that that's something you should look for. The Stommel model is a nice example of one, and whether or not the real world's Gulf Stream is going to shut down is something we'll find out. Whether it happens in the real world or not. It doesn't happen in all models, it happens in some models. So, whatever. That's the kind of thing you can wonder about. But all tipping points, too, are also signs of nonlinear dynamics, because it's the feedback parameter is uniform. It doesn't matter how big the amplitude is on a linear system. But the idea that you could go a certain distance, amplitude dependent distance, and then fall off onto another solution implies nonlinearity. So whenever people are talking about tipping points, that's also a nonlinear dynamical system concept. Linear dynamical systems don't have tipping points. Which is also why it's hard to guess where they're going to be and whether they exist. Because nonlinear systems are dependent on the magnitude of the effect. So you have to get to that magnitude before you see what it does. Unless you can guess it from putting together your continuum mechanics laws. Okay, so that's a good start on nonlinear dynamics. What about ODEs broadly? Those were the first two chapters, were ODEs and nonlinear dynamics. So the ODEs piece, we basically did exponential solutions, and then sines and cosines, and then realized that sines and cosines were also exponential solutions. And so those are essential. That's not all the ODEs you can solve by hand. There's certainly many, many, many more, but those are a really important one. And those are the ones that whenever we do a Taylor series, we tend to find those. So in retrospect now, you can appreciate why it's emphasizing that class of solutions. And so we can write it out with the the fancy integral form and the first order equation. We just have the solution for any linear first order ODE, which often ends up being an exponential. Or you can do the guess and check method if you think, oh look, this is a homogeneous ODE, I bet it's going to be an exponential, and crunch it through like that. Everybody remember those two techniques? That's basically what the takeaway message from the ODE section is. Then we add on to it bifurcation diagrams, the kind of graphing to understand how nonlinear systems work, the idea of local linearization around the steady state to get a sense of stability, feedback, all those pieces that we talked about in the nonlinear dynamics section. So are there any other questions on that stuff, or should we jump on? Yeah.
So on that graph over there, when you moved the branching part upwards, the bottom branch became unstable because it's between the other two?
Yeah, so I guess it's possible that it wouldn't have, but it normally would have. So I'm thinking about, so in polynomial nonlinear differential equations, the roots of the nonlinear polynomial is switching from positive to negative slope predictably. Like if you just think of a continuous function, so if I was going to plot x dot versus x,
Right.
and I drew a continuous function like this, all of my solutions are alternating between stable and unstable because I'm kind of crossing the zero axis this way, then that way, this way, then that way. So as long as it was of that class, you would have this stable, unstable, stable, because you were just cutting across back and forth. But I guess conceivably, since I didn't really tell you, I could have said that there was a discontinuity and did something fancy. I mean, if I was really wanted to get nasty nonlinear, I could have made them two stable branches next to each other.
Right. Or if the zero just doesn't dip below the axis.
Yeah, I guess you could have come up and just touched it and had a saddle point instead. So I was anticipating extra information that I didn't think which didn't have to be true, but I would have guessed it would have been true. Does that make sense, everybody? But we know how to draw this diagram. How do you make this? If I gave you a function,
You set the derivative equal to 0.
you set the derivative equal to 0, and that would be the roots. And what is this graph a graph of? It's just a graph of whatever that function is. So whatever that is, that's the thing you're graphing here. Because this is the x dot, and that's the x. So if I were to give you one of these, I would expect you to be able to draw this graph. Think about setting this to 0. Think about the steady states. Think about whether they're stable or unstable. It just depends on the slope as it cuts across. Because if you imagine a little perturbation in either direction, does it run away? So is this one stable or unstable? Stable. Because if I push a little bit this way, this says x dot goes up, which means I come right back. But this way it comes right back. This one would be unstable. So I would definitely expect you to be quick to do those kind of things if I give you some crazy function to think about it a little. Does that make sense to everybody? And then bifurcation and hysteresis would come after that. If we said, based on what this function was, you could draw a bifurcation diagram because it would probably have not just the dependence on x, but also a parameter. Off you go. Think about that. So what's different about second order? What about if I had two different x's, x and y, second order space? We actually went all the way up to fourth order space, but what do we have to think about? Everybody just wrote another one, dy dt equals f, and then probably make this one a function of x and y and r, and this a function of x, whatever. Two different functions, x and y and r. Can I make a simple graph like this anymore? Not really, because now the x derivative also depends on y. I could make a graph, if you gave me a particular value of y, I could make it like that, but instead, what we tended to do is we made basins of attraction, right, where we'd have x and y, and then we'd have flow fields that were going around, and fixed points, and things like that. So, you'll find the fixed points by setting both of these to 0, then solving that side. That will give you those. And then we actually talked a little bit about limit cycles and stuff, even though I think that's sort of like trajectories within that space and basins of attraction and things. We touched on some of those ideas, but we didn't do enough of it really that I would expect you to have more than a passing familiarity with what that means. If you find this stuff cool, you can take lots and lots of classes on this stuff, and you're definitely prepared for it at this stage. We talk a little bit about PDEs, which is the next section. Okay, so what's the difference between an ODE and a PDE? Or what kind of equation is this? An ODE. What kind of ODE is it? First order homogeneous linear. Right? I can make this a vector, and then we could raise the order if we wanted. Still homogeneous until I add something that doesn't depend on x. Then it becomes inhomogeneous. And for the first order, we actually have an exact solution for all possibilities of the linear system. For the nonlinear system, we have to play these games. Okay, so how do I make this a PDE? What do I need to have in there to make it PDE? I need a partial derivative and at least two of them. I need one that's like x and one that's, one that's partial time, and maybe something else that's like partial y, whatever, some other direction. And so that makes it a PDE. So what do we do with PDEs when we see them?
You try to separate them.
We try for separation of variables. That's one of the best starting points. And separation of variables, remember, goes like, suppose x is some function of y times some function of time, and you plug in and see if you can separate it out into ODEs. Frequently you can. And then when you do, then you use all your ODE tools. Frequently it ends up being an exponential again. So you're back to the same game that we've been playing over and over again. But not every solution can be written this way. So what are some of the things that we do to make this more general than that? We approximate on a computer, so we solve approximately, but one of the other things we do that's really important is we actually sum over a mess of these. Because if we find that these are sines and cosines, we know that the sum over of sines and cosines is a complete set. So any function can be expressed approximately with a long enough combination of sines and cosines. How do we know that?
Series.
Because we've already paid attention to it in Fourier series and we've already thought about it. So the Fourier series are kind of hiding. In fact, I think I mentioned this, but maybe it's obvious to you now. The Fourier series has that property because it is the solution to a set of equations like this, a linear partial differential equation. So too are the spherical harmonics. So too are lots of other weird function classes, Chebyshev polynomials, etc. So those complete sets come out of the Hermite polynomials, come out of the Bessel functions, the area functions, come out of solving this kind of system using separation of variables and then pushing it through and finding a complete set. And there's a broader class of theory about when that works and when it doesn't, but all of the systems that we've been studying, the heat equation, the Helmholtz equation, the Poisson equation, the wave equation, tend to be ones where this approach works pretty well. So it's a decent one to get started on. It also works for geodesy and kind of geopotential problems. It works for electrostatics, magnetostatics, potential vorticity inversion problems. Like there's a whole, like those kinds of simple problems involving this guy pop up a lot. Okay, so what's this guy? The Laplacian, what does it look like? How do we think about it?
It's like the double gradient, which makes sense, because the double gradient is
Yeah, so it's an operator that looks something like this. Maybe plus a z1 if you're in if you're in 3D. Oops. And it would act on something and take its partial derivative and x partial derivative. So why is this one special? Or can I write it a different way too? Can I write it in terms of divergence and gradient? Or curl? Curls are start with divergence and gradient, please.
non-versions of the gradient.
Yeah. So that's one. It's also a part of the curl of the curl. If you work the way through all of those triple product pieces, one of them, it's hiding inside the curl of the curl. But that table, which is hiding in between chapters, which I probably have not even printed out, is a useful thing to bring with you to the exam. The table of the triple product rules and all the things like, how do I take the gradient of A times B? Those kind of things, like it's nice to remember how that all goes. That little table helps you kind of manage your way through. What are the really important ones on that table? The ones that almost always come up on the exam. Back cap almost always comes up on the exam, and the double derivative versions of it. So, which is not quite the same as back cap, remember, because you can't commute the derivatives with the things, so you just look up the formula. You don't trust the back cap to work if one of them's a derivative. Okay, but the ones that are even more common on my exams anyway are, what is the divergence of the curl of a vector?
0.
0. And what is the curl of a gradient of a scalar? 0. These are really powerful. Frequently, this helps us clean up the PDEs we start out with, and you'll see, I think almost every exam has a version where using one of these helps you sort out the terms in the equation, and then make PDEs that you can do separation of variables and stuff. So definitely be on the lookout for these. Similar, what are some other tricks like this? These aren't quite tricks, but what are some other things that we've used to speed up calculation that we talked about? We did Fourier series a lot, and Taylor series. I was doing a Taylor series of a function, and that function had a particular property. I could immediately talk about which terms in the Taylor series would vanish and which wouldn't.
Do you like odd or even?
Odd or even functions. So this is actually kind of a differential version of odd and even functions. Because why this cancels is because of like just cross products of the derivatives commuting canceling. It's the same, it's a similar kind of symmetry built in. So odd and even functions frequently pop up as something that's like a quick way to sort of say, oh, I've got a really complicated equation, and then I'll say, given the fact that such and such is an odd or even function, what can you say? And then you'll say, oh, now I can go faster and go farther, that kind of thing. One of the other useful things to think about is how odd and even functions behave far away from the origin. What are the possibilities? talked about this before, but this comes up a lot as well when you think about dynamical systems. So, this is my function. This is x. So if the biggest term in the polynomial is even, what can I say about its limits as x goes to plus or minus infinity? The same direction. It can either go double up or double down, but it can't go up on one and down on the other, because that would imply that the biggest term is odd. Everybody got what I mean? And similarly, when I get close to the origin, I might think about the lowest order term being the dominant one. So out there, it's like x to the biggest power, and here it's like x to the smallest power is the one that dominates on this side. So you can think about, whether it's going like this, or like this, or like that, those kind of things, just by paying attention to the other term on the other side. Does that make sense to everybody? You can play similar games with the sines and cosines and think about, whatever. Which things are dominant under what limits. Oh, so what's more wiggly, an integral or a derivative? Derivative makes things more wiggly because it tends to amplify the higher terms in the Fourier series, and an integral tends to make things smoother. And we also know that because the way we write an average, which is definitely a smoothing operator, one of the ways we can write it is with integrals, right? We integrate whatever it is we want to average times the domain over the integral just over the domain. That works in 1D, 2D, 3D, n dimensions for a spatial average, right? Yeah.
One thing that confused me about that, I think we talked about this as being an exception to that, but if you take the derivative of x squared, it's 2x.
Yes.
And then you take the derivative again, it's 2. That seems to be getting less than.
It is getting less wiggly, which is part of, yeah. So in natural systems, which have noise in them, you don't expect so if I was measuring x squared in the real world, I'd be measuring x squared plus noise. And then I take the derivative of that. If I wanted, I'd get 2x plus the derivative of the noise. And this is really noisy, even though that isn't. And then if I take 2, the second derivative of the noise is in fact, this was white noise, like a Wiener process, as they're called. You can't even take this derivative because it's so noisy. So, in real measurements, they tend to have a spectrum of variability. And so even though we can think of sort of classroom examples, calculus examples, as soon as you get away from calculus and start thinking about chaotic or statistical systems, these guys are always there. So even though we're talking about things that might have exact solutions sometimes and sort of using that to motivate it, all of the geophysical systems we're talking about and all of the instruments that we might use to measure a geophysical system always have noise. So we're jumping, so that was why we built up deterministic, forgetting about this. Then we said, oh wow, there's chaos, even in deterministic systems, maybe we need something else. And then in the end, we decided to switch to statistics totally and just say, okay, everything's noisy, everything's uncertain. How do we quantify uncertainty? So that's a natural progression toward the kinds of systems we actually study, which is not only calculus, also statistics and noise in the system. Which is kind of funny that the way math is taught in the US is so calculus heavy that it's sort of like, to get to college, you have to be good at calculus. You need a year of pre-calculus and a year of calculus, and then you can, then you're gonna be ready for college. And then you get to college and you're like, I'm gonna take economics. So they're like, none of this is calculus, this is all statistics, and you're like, wait, what? Why did I take statistics? So I don't know. You guys know who Nick Kristof is, the New York Times columnist? So he takes college students on like a world tour, you write an essay, and the winner of the essay contest goes with him somewhere in the world to like experience like firsthand journalism, whatever. But he gave a list of the 4 things that all students should do in college, and the first one was take the statistics class and an economics class. He thought that was more important than what, those are really different, that you have exposure to that in college in a way that you don't in high school and the US system anyway. You don't get to see economics, you get to see like physics, and you don't get to see statistics, you get to see calculus. But his read is that economics and statistics are more important in thinking about how the world works. I don't know if it's more important, but I think it's underrepresented in the way it's taught. So, where else is that? So PDE, separation of variables, manipulation of the vectors. Oh, so what about continuum mechanics? So that leads us into those. So continuum mechanics, do they have any stray partial derivatives that are not built out of these divs, grads, and curls? Do you remember why we talked about div, grads, and curls and what's special about them?
The theorems.
They're the theorems, so you can integrate, you can do they have a fundamental theorem that goes with them. So absolutely, so conservation of something can be thought of in a divergence form or in an integral over the surface form. And because those two go back and forth, we frequently are thinking of stuff coming in and out of a box, and when you write that down in differential equation form, it has a divergence in it because of the fundamental theorem of calculus, the divergence theorem. And the gradient theorem, similarly, is a piece of that. The Stokes theorem, curl theorem is another one. So all of those equations of motion, all of those concepts like angular momentum or stuff going in, stuff equals stuff coming out, like conservation of mass, conservation of salts, conservation of water vapor, whatever. Those are all built from those fundamental theorems, and for that reason they have divs, grads, and curls in them. There's another reason, which is related to the fact that divs, grads, and curls are all special. They're vector operators. They have the same symmetries as vectors do. So remember, we showed that if you rotate the coordinate system, vectors don't change. The concept of a vector is the way you write it, component by component changes, but like it doesn't. The object doesn't care how we decide to draw a coordinate system. So we spent a lot of time thinking about different coordinate systems, and scalars don't change, vectors don't change, but the components change. So these differential operators also share those coordinate independent properties. And so that's another reason why they appear, is that it's sort of, they are the symmetry preserving forms of like x derivatives and y derivatives and z derivatives. Does that make sense? So that's why they're also there, because like a liquid is the same in every direction, or an isotropic liquid is the same in every direction, so it should only have operators in its equation of motion that don't care about where you draw the coordinate system. So divs, grads, and curls have that property. And so we talked about the heat equation and the wave equation. So I think the main reason why we talk about continuum mechanics here is to connect the idea of conservation principles to the heat equation, the wave equation. Those PDEs we learned how to solve a little, or at least we tried separation of variables on. So those are generated from the equations of motion for a solid, a liquid, a gas. You can get from one to the other. That's the idea. Okay. Any other questions on continuum mechanics, or should we
think it might have been Richie that was teaching us, but we talked about like if you had things mixed within like a area but I don't know that we ever had like a homework problem on that or
Oh, right.
covered any of that.
Multi-phase continuum mechanics.
Yeah.
Yes.
So how much should we be able to do?
It is nice to know that the conservation of mass equation can be adapted to have conservation of multiple classes of mass within an area.
Okay.
That's a nice concept to have in your brain. We're not going to use any more of it than that.
Okay.
The continuum mechanics, Victor Tsai and Chris Huber are teaching a full semester on continuum mechanics next semester. There's a lot more to say than what we can possibly say here. Really, the only point I want you to get is the importance of the Div-Grad and curl theorems, the fundamental theorems of calculus and construction of those equations of motion, and then the fact that under limits where we can linearize those equations of motion, like non-turbulent flow and things like that, then we can get back to the heat equation and wave equation that we learned how to solve. So it's really the relationship between those linear PDEs and the physical PDEs is the real, that's where I'm hoping that you're just making that connection. More than having deep insights about continuum mechanics, which, whatever. In grad school, I took 6 classes on fluid dynamics or something. So it's like, and I don't feel like that was enough. So it's, this is the kind of thing that you can really think about a long, long, long time, and it just gets, they're very deep equations of motion. They're much harder than the heat equation and the wave equation that we solved in class. So this is just an introduction, a very light gloss of what they mean. Yeah.
So how is continuum mechanics related to fluid dynamics?
So the conservation of mass and conservation of momentum, those continuity equations, so, d rho dt plus del dot rho u equals 0. That's just the stuff isn't going anywhere. The conservation of mass based on density. And then d rho u dt plus del dot rho u, sorry, this is the double vector, it's a tensor, equals forces. Or actually, I mean, more than that, I can say is the divergence of a stress tensor. This is true of solids, liquids, and gases. Conservation of mass, conservation of momentum. What's different is this guy. So a solid has, if you displace a solid, not a displacement like this, but a displacement trying to pull it resists. And so solid mechanics are written in such a way that this guy allows solid body motion, but doesn't allow deformations. And so this is like a divergence of a deformation that then drives a response, or an interesting response. Liquids don't resist deformation, they resist the rate of deformation. So if stuff is squishing by itself, then there's a resistance form over here. It gives that. And then gases don't even resist compression. So liquids resist compression, but they don't resist shear, or they resist shear, the rate of shear, not the shear itself. Solids resist compression and shear, and gases don't resist any of those as strongly. They allow them all somewhat, and then there's just a little correction to it. So all of continuum mechanics is in those two equations, except for the fact that you don't know what the specific form of the stress tensor is.
So would you say that fluid mechanics is continuum mechanics?
Fluid mechanics, solid mechanics, gas mechanics, plasma dynamics, magnetohydrodynamics, all of those are all different flavors of continuum mechanics. Geophysical fluid dynamics. Yeah. And the key thing for geophysical systems are, for solids and the mantle, things like that, how you make this stress tensor. It's really, that's the most interesting part of that story. And in atmosphere and ocean dynamics, it's the rotation of the planet and the stratification. So the density is not constant, it varies everywhere in the vertical in particular, but actually everywhere in space. And the fact that I wrote the non-rotating form, but we could have a Coriolis force in here, and then off it would go, the rotating form of the momentum equation. Yeah.
I don't think I've ever understood what a tensor is.
Oh, that's a good question. So that thing I was saying about the symmetry of space, that's, a tensor is something that obeys that. So it is like a vector, but you could have, one example of a tensor is just two vectors sitting next to each other where you interpret it as the multiplication but not the dot product. So it's sort of like a matrix, where this would be u1, v1, u2, v1, etc. That's an object that is a tensor. But it has special symmetry properties because of the fact that these are two vectors that are inside of it. So a tensor is like a matrix, or like a vector, or like a scalar. Actually, a vector and a scalar are examples of tensors. But you pay a lot of attention to how they transform as the coordinate system rotates, or dilates, or contracts. And this is something that I would love to have more in this class of, but it's unfortunately very, just the notation that's used to explain tensors is really non-intuitive. And so it's a bit hard to squeeze it into this class, but I've been thinking about whether I can do it better. But the main idea is that it's something like a vector or a scalar or a matrix, but that it understands how our physical space, our pseudo-Euclidean physical space, rotates and transforms.
How can a scalar be a tensor? Like, where do you get symmetry in a scalar?
Oh, so the scalar is just the same regardless of which way you look at it. So a scalar is a tensor that has no dependence on the, they're all the same, all scalars. So tensors, a 0th order tensor is a scalar, a 1st order tensor is a vector, a 2nd order tensor is like a matrix, but a special kind of matrix that's like the product of two vectors, but the outer product's not the dot product. And then the 3rd order and 4th order and so on. But they're sort of funny objects that you can make like that. And they have all the symmetry properties of this physical space. And you can do things to them, like you can take their divergence or their gradient, and it makes sense because divergence and gradient operate on things that have those symmetries, and they preserve those symmetries. So it's like tensors are the building blocks of continuum mechanics. They're the building blocks of all field theory, actually. It's like they're the things that, when you want these equations to be symmetrical in the right way so that they represent our physical world the correct way, you build them out of tensors and tensor operations like diff, grad, and curl, and everything is okay. Yeah.
What, like, can a tensor essentially just be an array? Like, what makes it?
So yeah, so that's sort of the difference. So it's a little confusing because we also use vector and matrix in the array sense, like the way that MATLAB means it. Like a vector is just a list of things that you're going to operate on with a linear operator. But that's not, a tensor is like the specialized one that's specific with one component per direction of space, and it has built into it the idea of a particular dimensionality of space and rotations and reflections in that space. So an array of say 10 elements with, if you took 10 experiments and you wrote them down as an array and you wanted to think about their statistics, that's a perfectly valid thing to do, but it has nothing to do with tensors. Yeah. Even though it might still have something to do with vectors. Okay. Because vectors in the array matrix sense of vectors and matrices, the linear algebra sense is divorced from the geometry of the underlying space. Tensors go the other way. They're all about the geometry of the underlying space. And that's the sort of difference. But frequently you mean the same thing, and I'm often switching whether I say vector or tensor when they are interchangeable, which is probably super confusing. But I'm normally thinking like about symmetries or thinking about linear algebra when I'm using the words. Does that make sense?
Yeah.
So you guys figure out what the difference between algebra and calculus is yet? This is one of the ones that I'm like, I asked my sons, so they're in 9th grade and 11th grade, and they were like, what? I was like, don't you know you're taking these classes, what are they about? They were like, I don't know, we just do the problems. Like, tell us the problems, we do them. And I was like, yeah, but what is algebra? What is calculus? And they're like, what? So anyway, you have a sense?
I mean, calculus has to do with the rate of change of functions, and algebra just has to do with the manipulation of them.
Yeah. Calculus has limits in it, is one way to think of it. So there's the notion of a infinite sequence or series, and the limits converging to something. Algebra doesn't have the notion of limits at all, but calculus is so heavily dependent on algebra that it's hard to tell them apart because you're always using algebra when you're doing calculus. But algebra is the part before you get to the limits. And so derivatives are really important flavor of limit, as are integrals. So that integral differential calculus is built on top of the limiting case at the beginning, the underlying piece. And what's statistics?
How to interpret data?
How to interpret data.
Averages.
Averages, variances. So it has important metrics in it, which you can study and think about how they behave. It has the notion of probability, closely related. Most of the time they call it probability and statistics. So statistics is the manipulation of averages and variances and things like how do you think about those. Probability is the notion of probability density functions, probability distribution functions, how you think about those, what it means when you take an experiment, if you have some randomness, what does it mean to be a random variable? Does it mean uniform probability distribution? Does it mean something different? Those are the kind of concepts that come in statistics and probability. Yeah.
I just had a question about whenever we did the homework problem on why nothing is signed, the scientific.
Oh yes.
Are we supposed? Is that supposed to mean that all the recent stuff with all the recent climate change studies that are coming out, just take them with a grain of salt? Is that what that's saying, or?
No, not exactly. That's exactly the point. Is I think that's the first cut. Is oh my God, everything is wrong. But Gene's point. But science is getting better at making things. Our predictions are getting better, so that can't be true in the general sense. What I'm hoping you are going to take away from that is to continue thinking about that and thinking about the specifics of the pieces he's griping about. Not the general problem, because it tells you that some classes of problems are not well handled in science, and others are just fine. And it has to do with the kind of experiment you do, your experimental design, and the way you use your statistics. So what he's really griping about is p less than 0.05 equals statistical significance. All I need to do is just put it into R, gives me a p-value, and I'm done. That's exactly what he's saying don't do, because you can certainly design experiments where that statistic is totally happy, tells you statistical significance in the surface level is there, but when you think about what the underlying meaning of that really was, it's not there. So that's the important thing, is it's why you need to learn statistics and probability, is because it's easy to design a scientific experiment and maybe a pseudo-scientific experiment that look the same and that have the same metrics of success, the same statistical semblance on the surface level, but then when you think about what they really meant, they actually don't have the same meaning. So you guys know this joke about lies, damn lies, and statistics. There's 3 ways of lying. There's lies, damn lies, and statistics. So people misuse and abuse statistics all the time because most audiences do not have a sophisticated understanding of what a statistical claim actually implies. And so they are very easy to convert into lies because people just, whatever, 5 out of 4 people don't understand fractions or whatever. Like there's, it's one of those things where it sounds really good almost when it's not good. Like you could, it would be fun to come up with statements. Actually, this could be fun. Come up with a statistical statement that sounds true that is definitely false. Like that kind of thing is a good, so that's what I think I'm hoping you take away from that is you need to think hard about what statistics mean. You need to be careful in selecting statistical metric for the problem you're working on because you definitely can go wrong, and especially when the other life circumstances of like promotions and desire to get a positive result, and you want to write down something in your paper that's meaningful, so you go with the thing that has the statistical significance metrics all positive, but you really shouldn't, without thinking about whether that one actually signified how you were interpreting it. So it's really a question of interpretation, not a question of science can't do anything. Does that make sense? Yeah.
Just out of curiosity, like looking historically, do we think that the statistics that we have are adequate enough in that if a study in the 80s measured some random variable or some value or something, and then we got better measuring tools, it's do those measurements always fall in within the plus or minus bars?
No, I mean, everything's always an approximation in statistical measures, and the error bars are definitely part of that. And you can find pathological systems, chaotic systems is a good example, where it looks like you have either greater or lesser uncertainty by things that assume like independence. But when there's not actual independence because there's chaos, you don't really have independence, even though you might have approximated it to get an error bar. So, and there are real world consequences. Decadal forecasts, I think people are doing a lot of research on how to do decadal forecasts. So in between climate change timescale and weather timescale. You can't do it everywhere, but in some parts of the Earth, there's predictability on the 10 to 20 year timescale, which when I was a grad student, everyone said that's impossible. There is no way that exists, but it does. And now we're trying to use it because it would be really great if in some parts of the world you could say the weather's going to be rainy for the next 10 years. Then you do things differently with the way you manage water. And so that's an example where we would have put the previous limits, knowing that it's a chaotic system, knowing et cetera, we would have said that's not possible. But now, having better models of a full nonlinear system, we can see there actually is some lingering predictability. So, yeah, it's constantly in flux. But I wouldn't say that old is bad, or new is bad. It's just, you need to use your brain.